Now I'm going to talk about an important concept that I use not only in principles of macroeconomics, but also intermediate macro and international finance or international macro. And that's the aggregate expenditure model, which I'll talk about in the next video. Right now I'm going to talk about the connection between consumption and income, and how, because consumption is part of income and income drives consumption, they lead to this magnifying or multiplier effect. So I'm going to show you the consumption function and how that can lead to changes in spending, changes in consumption, leading to changes in output that are actually greater than the original change in consumption. So then I'm going to add government and add investment in a later video. But both of these are going to show this connection that increases in spending increase GDP, decreases in spending might lead to decreased GDP. So we start out with what is called the consumption function. This is C equals A plus BY. That's related to slope intercept form. Sometimes you see Y equals MX plus B. But here, this is actually not the Y-axis. This is the horizontal or X-axis. It's a little confusing. But basically speaking, there's an intercept and a slope that says that as income rises, consumption rises. Autonomous consumption is auto, like an automobile drives itself. Auto means self. This is self-directed. It's independent of income. If income is 0, consumption is A. That's the intercept. B is the slope. Now that is what's called the marginal propensity to consume, or MPC. What that is MPC is changes in consumption over changes in Y. In other words, if Y goes up $100 and consumption goes up $90, that would mean it was 0.9. Usually this is a decimal between 0 and 1. All right? And sometimes there's another one called the marginal propensity to save, and that's the fraction that is not consumed, it's actually spent. And so sometimes you can say MPC, marginal propensity to consume, plus MPS equals 1. In other words, of 100% of income, the percentage spent and the percentage consumed must equal 100%. But again, we usually do it as a decimal between 0.00 and 1.00. So this is the consumption function. Now, what does this mean? Well, the way I look at it is that if you have income as your horizontal axis, you are going to split this income one of two ways. It's going to either be consumed or it's going to be saved, and that's important. The more that is consumed, the more money is spent in the economy. Once it's saved, it disappears from the economy. It's not used anymore. So how much of this income is spent and how much is saved is actually the slope. It's rise over run. So I'm going to draw it at about 0.75. If you look here, this is 3/4 of the way up. If I make a line here, this could be my consumption. As Y goes up $100, this could be consumed, and the rest would be saved. And that would be the proportion or the fraction that is consumed of additional income. So remember, marginal means additional. Propensity is the likelihood. This is the likelihood to consume $1 that is earned. Is it all of it? Is it 0? Is it somewhere in between? And this is rise over run, C over Y. That's the slope. So that is going to be where we get part of the line that makes up our model. Now, next thing we have to do is say, well, what if this changes? Now, if you were to save 100%, you would actually have a steeper line, and that would be the steepest you can get is a slope of 1. And that means that spending is exactly equal to income. All right, but if it's less, it's going to be less steep. And so how steep it is has to do with the MPC. All right, so that's important. Now, there's a couple more concepts. First of all, we're going to find that at $1 of spending doesn't just lead to $1 of income. Because remember, Y equals C plus G plus I. Now, I'm going to leave off the X and M here because this actually changes the slope. Now, a lot of international economics books will say that if you have consumption and savings, there's actually a third propensity. It's the marginal propensity to import. That means that if $1 earned, it could actually mean that there's 3 things to spend it on, and imports is the third. The more you import, the less you consume of domestically made products. And so if you add imports, it actually makes the slope less steep, because it actually changes the multiplier, and it changes these things we find. So I'm just going to have 3 parts of it here. Y equals C plus G plus I. Now, what we're going to find out is that if you add G and I, it just makes a parallel shift up, but it doesn't really change anything. So unlike exports, investment and government don't really do anything. So it's just going to make it higher, but not any change to the slope. So we have this equation here. Now, what I'm going to do first is I'm going to lay this out algebraically. If I bring back C equals A plus BY plus G plus I, and I do it in alphabetical order. Some people do I first and G second. You can algebraically switch this and basically have this. Y over 1 minus B equals A plus G plus I. All right, and the last step is this. Y equals 1 over 1 minus B times A plus G plus I. In other words, if you increase any of these parts by $1, it's going to be multiplied by this fraction here. And so we're going to lay that out. All right, so I'm going to use the numbers over here to show that. But the big thing is that here, if you have $1 of income increased over here, it's going to multiply by this part here, and then Y is going to go up by a disproportionately large amount. That is the multiplier effect. All right, so how does this work? The way I think of it is that if you put $1,000 of money into the economy, you'll put it in the auto industry. Auto workers get paid, they go out to eat. So that $1,000 gets partially saved and partially spent. And then finally it goes into the economy a second time, a third time, a fourth time, until it shrinks away through savings. So $1,000, if half of it's saved, becomes $500 somewhere else, and someone else takes that in as income. And so someone gets a $500 paycheck, they save half, they're going to spend $250. And that's what these numbers show here. I have multiple rounds. This $1,000 gets spent and respent and respent. And because I have a number made up of 0.5, that means that half the money is saved. I'm going to do a second time with 0.9, which means more is spent and only 10% is saved. We're going to get different numbers. Now, this is what happens. $1,000 of additional spending. It could be consumers feeling good and spending. It could be a government program. It could be businesses investing. Somebody spending more money will do this. Now, traditionally, you could start with simply consumption. And if you start with consumption, you can say, well, make a simple model and add government later. So consumers spend just $1,000 extra. Round one is spending. The second round, $500 gets spent, because if I get paid $1,000 and I go spend $1,000, someone gets $1,000. If that person is going to save half, and so we're now adding two different people spending the same money twice. I spent $1,000. Nobody's taking that away, but someone else is getting paid $1,000. They're spending $500. We've already multiplied 1,000 into 1,500, but it keeps going. Saving half, the third person spends $250. They're spending half of 500. Half of that is 125. So another person gets a paycheck of 125. Another person gets half of that, what is not saved. So $62.50 all the way down. Now I stop at 6 and I go to 18. At round 18, it's a penny because it's been divided by half over and over and over. Right? So at 18 rounds, it's pretty close to as high as it's going to be because it's going to keep getting smaller. This adds up to $2,000. Okay, so it's $1,000 doubling with an MPC of 0.5. Right? But what about here? Now, if you look here, 1,000 becomes 900. Already, it's $1,900, where the different MPC was 500. In other words, an MPC of 0.9 means that more is spent every single round, which means it shrinks less quickly and it can go more rounds. Each round is bigger and there's more of them. So instead of 1,500, 250, so forth, 1,900, 810, which is 90% of 90%, 729, 650, 610, all the way down to around 111 rounds, and that's just randomly off of what I calculated. It's below a penny. So this money was spent over 100 times, shrinking each time through savings until finally it reaches a zero additional contribution. This adds up to $10,000. So that's the multiplier effect. It comes from the same money being circulated through the economy and spent and respent over and over and over again until finally it's shrunk down to nothing through savings. If you have a higher MPC, you have more money being spent more times. Now, this is not a coincidence. How does doubling, like if you look, this is doubling 1,000 into 2,000. How do you turn these numbers into double? Likewise, $1,000 becomes 10,000. That's 10 times. It's no coincidence that 0.5 leads to 2 and 0.9 leads to 10. That's because the formula is 1 over 1 minus MPC. If you have 1 over 1 minus 0.5, which is basically a geometric progression in math, this becomes 2. 1 over a half is 2. Likewise, 1 over 1 minus 0.9 is 1 over 1/10. If you flip that fraction, you get 10. In other words, the multiplier effect. This is the multiplier. You can turn $1 of original spending into $2 because the multiplier is 2. You can turn $1 of original spending into $10 total, or 1,000 becomes 10,000 because of this multiple spending. And so a higher MPC means more spending. It means a higher multiplier. All right, so that means that how much we spend can mean that $1 spent by some group of people leads to more money of GDP overall. All right, so this is the math behind it. A consumption function with a slope intercept form, where autonomous consumption is where you start positive spending even if income is 0, but spending rises if income rises. It depends on the slope. This B is the marginal propensity to consume, and that's the slope. And then you can algebraically solve and find a multiplier, and we showed that if you put $1,000 into the economy, it does multiply according to this formula.